Welcome to the Astrophysics Podcast. It might surprise you to know that a lot of the universe is basically a fluid. That is to say, most of the phenomena we see on large scales is made up of gas that flows and shears and obeys the laws of fluid dynamics. Stars behave like a fluid, supernovae expand like a fluid, the planets form out of a gaseous disk that flows and shears, and even galaxies move like a fluid. As a result, a lot of astrophysicists develop tools to simulate astrophysical systems using the equations of fluid dynamics. I'm actually one of those astrophysicists. When I was a graduate student, I developed some codes and computational methods for evolving the fluid equations on the computer, and I've been using those codes ever since to simulate astrophysical systems, everything from the formation of planetary systems to the explosive death of stars. You may have seen simulations like this before. I mean, you haven't seen any of mine. I don't have that kind of press team. But if you've ever watched an animation of the formation of the first galaxies in the universe, it's likely you're watching a fluid dynamics simulation like the world-famous Illustris simulation, which took everything we presently know about dark matter, fluid dynamics, and gravity and put them all together to see whether it could naturally generate the kinds of galaxies we see today. My guest today is Dr. Yuan Li, professor of physics at the University of North Texas. Dr. Li is another expert on fluids, and one of the many things she studies is turbulence in the universe. That's right, turbulence is not just something you experience on planes or while whitewater rafting. It's generally a phenomenon that occurs anywhere there is a fluid that's being stirred up in the atmosphere, in the ocean, or even out in space. And it's a meaningful question to ask whether the turbulence we see out in the cosmos obeys the same kinds of laws as turbulence you encounter in an airplane. I mean, why not? Like me, Dr. Li studies a wide range of topics using her codes, and since fluids are everywhere, she has interesting thoughts about all kinds of phenomena in astrophysics. I'm Paul Duffel, and this is the Astrophysics Podcast. It'll be fine. All right, now I have to do my intro, right? Ready? Okay. Welcome to the Astrophysics Podcast. I'm Paul Duffel, and my guest today is Dr. Yuan Li, professor of physics at the University of North Texas. And Dr. Li, thank you for being on my little podcast.
Thank you for having me, Paul.
Good. We've known each other, about 10 years now?
Yeah.
That's crazy. So I met you first, you were a postdoc at the Center for Computational Astrophysics, were you? Or is that when we first met?
Yeah, maybe.
Okay. You don't have to know the answer to that question.
I've known of you for a very long time.
Oh.
Like, people talk about you.
Oh, well, that's nice to hear. Anyway, good. That was good. You know how to make me happy. Good. Well, okay. Anyway. But good. Anyway, but it's much better to actually meet you. I want to start by talking about you personally and how you grew up to be a scientist before we talk about the science. So let me start by asking, where did you grow up?
I grew up in a small city in China.
A small city in China?
With 3 million people. Last time I checked, more than New Zealand.
Okay. So a little tiny...
Yeah.
city in China. I'm not going to be... What was the name of this city?
Anshan.
Okay. And so what was that like?
I think it's sort of like Detroit.
Sort of like Detroit?
Yeah, and that it's got a lot of heavy industry. Yeah.
Okay. And what was it like for you? I don't know. What was your growing up in China? I don't know anything. I don't know what it was like to grow up in China.
We were poor.
Oh, really?
Yeah. Well, I grew up in China.
Okay. Well, well, I don't know.
Yeah.
Okay.
I didn't have a lot of toys. That's what I tell my son all the time. I didn't have a lot of toys when I was growing up. Yeah.
Okay. So then.
But I was happy. I was happily playing with dirt, digging holes.
That's a great thing with
and
kids.
Bugs. I liked bugs.
Yeah.
I still like bugs.
Okay.
Yeah.
Well, those are some, bugs are some of the low-cost toys you can have for kids.
Yeah.
I do not like bugs.
Oh, what about caterpillars? My favorite.
Oh my God.
Caterpillars, the green ones. The green ones,
You would have been the kid that was scaring me with a caterpillar running around.
I was.
Traumatizing me. Okay. Anyway.
Yeah.
That's
but
good.
have you tried to touch one?
I have no desire to touch a caterpillar.
The green ones,
I'm sure the green
squishy.
ones are really nice. Yeah, they're good.
They're kind of soft and squishy and
Okay.
Cute, I think.
Okay.
Mm-hmm.
Well, I'll let you have that opinion. But so you're a little kid growing up in China and in a small city of 3 million people.
Yeah.
And so then, how did you get interested in science? Like, do you have a memory of the first time?
Yeah. So I think my parents introduced me to astronomy pretty early on. I remember my parents would show me the stars, the few stars we could see in the night sky.
Yeah.
My home city is heavily polluted.
Right.
I remember there was a time when I thought the Pleiades cluster was the Milky Way. I'd never seen the Milky Way growing up. And I knew it was a collection of stars.
Okay.
And
then you saw...
I thought, could that be the Milky Way?
Could that be the Milky Way? You saw the Pleiades cluster.
Yeah.
Maybe that's Milky Way.
It was a collection of stars.
The Milky Way thing people are always talking about.
Oh, I mean...
Yeah, no.
In the past, I mean, the Chinese people knew about the Milky Way.
Obviously. They were presumably the first ones.
When people in China could see the Milky Way. I remember being obsessed about planets when I was in elementary school. Mm-hmm. I thought they were cool.
What was your favorite planet when you were a kid?
I don't remember.
Okay. Mine was definitely Saturn.
Okay. Because
of the rings.
You know what? I think it might have been Mars because I thought maybe we could live on Mars one day. Yeah.
We could. Maybe. Mm-hmm. It's still a possibility. We don't put as much effort into that these days, but, it's still a possibility. Yeah. Okay, well, that's a good answer. Mars is a good answer. Anyway, sorry, I didn't mean to derail you by asking your favorite planet. but so anyway, you got into astronomy pretty young then.
I was interested in a lot of other things too.
Okay.
I think I probably. I think I told you yesterday, right? I ranked arts higher than astronomy.
Oh, okay.
When I was a kid. But I think when I was a teenager, I realized I would need to make a living, and I didn't want to be an artist.
Okay, you thought, but
it would have been a little risky.
Yeah, well, astronomy can be a little bit risky too sometimes.
True. I mean, in the sense that you may not end up being an astronomer, but you should be able to find a job, right?
Yeah. No, I agree with that.
Yeah. But if you're trained as an artist, I'm just saying, realistically speaking.
Well, there are people that do things that aren't necessarily art. You might not define as art, but they're trained as artists, and now they do motion graphics for some company, or they do design logos and things. So maybe it's not exactly what you would like.
Maybe harder for musicians to be.
Maybe. I don't know. I haven't tried. I mean, I'm not a musician, so I don't know. I'm sure it's not easy, but yeah.
Yeah.
Okay, good. I'm not sure where we're going with this. That's okay. So then,
you can cut it.
No, this is gold. What are you talking about? This is all anyone wants to hear about. So okay, so then, so you were saying your parents, there were influences on you as being interested in science.
Yeah.
But so it's interesting because a lot of times, like if you grew up, if you grew up and your family didn't have a lot of money, they might want you to work on something that's a little bit less highbrow. They might want you to do something that's a definite. So
we were poor, but in a not relatively speaking.
Okay.
So everybody was poor.
Right.
Yeah.
Okay.
My dad is an engineer.
Okay.
So,
I see.
Like, it's not like we were eating dirt.
Right. Okay. Good. Well, you painted a picture in my head, so you didn't have any toys, so you just played with dirt. So, like, anyway.
But all the other kids were also playing dirt.
Okay.
Yeah.
Kids like dirt. Does your kid like dirt?
Not really.
Okay. Yeah.
No.
I actually didn't either.
But he has toys.
Yeah, you can buy him things other than
I wish
dirt.
he was more into bugs. Like, I would love to share the love for caterpillars with my child.
That's unfortunate.
It is.
That's like, Anyway, so they were interested in you, pushing you towards science, or
No, I think they just wanted me to be exposed to all kinds of interesting stuff. I mean, they also introduced me to arts, right? So I think maybe they would have been fine if I had decided I really just wanted to try it. I wanted to try to be an artist. They didn't say, oh, well, it'll be hard to.
Right.
In fact, I think my mom said, oh, you'll be fine as an artist too. Like, worst case scenario, you can just teach arts, like as a teacher, and still be fine.
So they were generally supportive.
Yeah, they were very supportive. Yeah.
You as long as
mostly
you were,
my mom. Yeah, my dad was. Well,
your dad
let's not talk about my dad.
Oh, okay.
He's a pretty stereotypical Chinese dad.
Okay.
Pretty hands off, yeah.
I see. Well, this was not intended to turn into a therapy session,
yeah,
so
exactly.
I'm mostly just curious about how you grew up and how you got into, like, how you moved from that into science. So when did you first get into, like, did you major in physics? You presumably majored in physics in college?
Oh, actually not. But that's a whole nother story.
Oh.
But, yeah.
It's a whole nother story.
Yeah, it's kind of complicated.
Oh.
Yeah. Well, so I wanted to be an astronomer, but they only wanted one astronomy student from my province that year.
Oh. Wow.
That's how things work in China.
Okay.
Yeah, and then you have to basically choose your university first, and I chose a very good university, and then they decide what you're going to study.
So wait, then
It's a very strange system.
No, I'm really interested in this. So that one person from your province could go into astronomy.
And there was another kid who scored a little bit higher than me.
Oh my God.
Yeah, but I think they actually ended up dropping out of the program.
Okay.
I actually don't know for sure.
Well, I'm not expecting you to follow up on every.
Yeah, I didn't get into astronomy.
So you didn't get into an astronomy program because you weren't the number one person in your province
that picked that university
that
major.
And that major. So then where did they?
And then they put me in atmospheric sciences, which is close enough. I mean, you learn fluid dynamics and stuff. So.
Okay,
but I wasn't interested in, like, predicting. I was mildly interested in climate change, but I think most people would end up doing weather forecasting, and I just don't care enough about it. And you just, you carry an umbrella and you're fine.
Okay,
that was my attitude.
That was your. I see.
Yeah, I wanted to dream big.
Okay.
I wanted to study the universe, and so then I took a sort of a detour and still ended up doing astronomy in graduate school. So I did a master's in China and then applied to graduate school here in the US. Yeah.
So wait, when did you transition from planetary science or atmospheric science? That was only when you came to the U.S.?
No, when I did my master's.
When you did your master's, you said, okay, well, now that I've gotten this degree in planetary science, I'll get my master's in physics or astronomy.
Yeah,
okay. Okay. Okay, and then you came here, and then wow, that's so you really had to go around all these channels in order to actually.
But in a way, if you go through a normal physics department, you probably don't even learn about fluid dynamics. So I'd say it's a blessing in some ways.
That's true. I mean, I mean, I didn't study fluid dynamics when I was in college.
Right? Yeah.
And I would have. Now that's all I do for my research. So.
Yeah, right? So, and we don't really use quantum mechanics, not that much.
We don't, but some astronomers use it. But okay. So it ended up working out for you, and you had enough. It actually kind of gives you a unique background that probably helped you in many ways. Maybe.
Yeah.
Okay.
Oh, I can predict weather really well.
Can you?
Seriously. Yes.
What do you mean by that?
Well, I can look at the sky and tell you how likely it's going to rain in the next hour.
Just by eye, you kind of see.
Yeah. I got that training.
I didn't realize that came along with an atmospheric sciences degree. Is you can just kind of look at the clouds and the.
Yes.
And you can see whether it's going to be.
Yes.
Okay. So why do we have these satellites up there then?
Good question.
Okay.
What do you think the satellites are doing there?
Well, okay. All right. Well.
Oh no, it's. Yeah, I'm probably not as good as satellites, but well.
I assume that they're more precise.
Wait, complementary. We have complementary strengths.
Okay.
Yeah, me and satellites.
Between you and satellites.
Yes.
You can do a pretty good prediction.
Yeah, well, because you see from the ground, and the satellites.
So wait, is that? Of course, this is not astrophysics, but is that how weather
close.
Prediction works? Is like they have the satellite data, but then the meteorologist will also kind of.
I don't know, right? I never worked for real. Yeah. So.
Okay.
But I could. So it's. There's science behind all this.
Right. It's not just kind of like you. It's not just you feel it in your bones. And it's kind of,
no, it's kind of like machine learning in a way, almost.
Except it's
but then there's also
learning.
science.
It's human learning.
Oh yeah, it's human learning. But there's science behind it too. So, for example, you can look at basically the optical depth of the clouds.
Okay.
And that. Okay.
Well, in other words, how opaque the clouds are.
How opaque, yeah. How gray the clouds look. And that gives you a sense of how much stuff there is that's about to pour down.
Okay.
Or not. Yeah.
Okay. Well, that's good. Anyway,
Well, I hope everybody learned something. I don't know.
Well,
that's that helpful? Yeah. So basically, if the clouds look thicker, then it's more likely to rain.
Right.
It's common sense too.
Right. Yeah. I mean, that much I was vaguely aware of. Although, like, I guess I don't have a sense of how to tell the difference between different clouds and whether But yes, I agree. Like when there's a big dark cloud, you assume that that's a rain cloud and it's going to. Yeah. Okay. So it's that kind of thing, but a little bit more training.
Yeah.
Okay. Well, that makes me feel a little more satisfied. It's not just you having some kind of magic power.
No. I do also.
You also do magic powers. Oh, good. Good to know. Anyway, so then that's how you got that's your sort of path that you took along the way to astrophysics, and then you studied it here in the U.S. in grad school at Columbia University.
Yep.
And we were both in New York City at the same time. You did your PhD at Columbia while I was doing it at NYU.
Yeah, we never hang out.
And we never hung out the whole time. We totally would have had fun. You were past your caterpillar stage, so you wouldn't have scared me off with that.
Yeah.
But when New York City, people way up north don't come down to.
It's a shame. Yes.
But that's okay. We eventually found each other. So. Okay. Well then, so why in particular do you like astrophysics? Why not something else? I mean, I know we kind of said like you wanted to do it, but
it's cool.
It's cool.
Yeah.
That's good enough answer.
Yeah.
Okay.
Yeah, isn't it obviously cool?
I think so.
Yeah, so
Probably anyone listening to this probably thinks so.
Yeah.
Who would click on a thing called the
Yeah.
Astrophysics Podcast
Yeah.
if they didn't think...
yeah.
All right. Well, I guess I don't need to justify that. Fine. We'll move on to the next question. So, here's a question for you. When do you feel like you learned how to be a scientist?
Oh. Have I?
Have you?
I'm still learning.
Well, okay. But you don't. I mean, do you like? I don't know. Do you like? I guess the question is meant to be interpreted how you feel like, but you don't feel like.
I think I'm still growing as a scientist. I'm still learning to be a better scientist every day.
Okay, and
That's how I feel about it.
How do you define that then? Like, what does it mean to be a good scientist?
Oh, that's a tough question. To have better ability to understand nature,
Okay.
which is what ultimately what scientists are trying to do, right?
Sure.
And I think I'm still learning new tools and new skills. That's why I think I'm still growing, even just as a researcher. And I definitely am learning to be a good mentor, a good teacher, and I think all of those are also part of being a good scientist.
Okay.
Yeah.
So it's not just about being able to like do
good research.
Yeah. It's about how do you communicate to others and how do you how do you teach the next generation.
Yeah.
Okay. So anyway, that's interesting. So you feel like you're always learning more about how to be a good scientist. That no one has yet given me the answer, so maybe everyone else has already figured it out. I like that answer. So then, okay. So now you're an astrophysicist. Well, apparently, maybe you're not, but now you're an.
I am.
Okay. But you could always be better.
I'm also a scientist.
Yes. But so, what are some things that you like the most about your job?
Oh, okay. I think I really like research. That's the honest answer. And I do like working with students too.
But so you just like what about research do you like?
Just figuring things out.
Okay.
I think, yeah.
Like you have a problem and nobody else has figured it out.
Yeah.
And it's something like you can kind of.
There's that, and then there's also just appreciating the beauty of this universe. In a way that's similar to just us appreciating a beautiful painting. But of course, we understand the universe in a little bit different way.
The way we appreciate it is different.
Yeah, but it's similar in the sense that maybe it's not necessarily about figuring out an answer to a specific question, but just to feel, oh, this is so beautiful. Right?
Sure. Okay, so then, and that's a great thing about astrophysics is it's like almost anything you work on in astrophysics has just kind of incredible scale and power to it. Okay. And then, so is there any? Oh, I know you'll have an answer for this. And we may, but is there anything you don't like about your job?
Oh, why is that? Can you? You need to update that list.
Is there anything that you don't like about your job that you're willing to say out loud?
I need to think about it.
Okay.
Jet lag. When I travel.
I see. So, by the way, thank you for coming to Indiana.
A whole hour jet lag.
But yeah. So just generally like being expected to travel for lots of things, and then
I like meeting people at conferences and talking to people, but the traveling itself is tiring, and I
totally agree with
don't
that.
do well with jet lag. So if somehow we could make that part disappear magically, that would be nice.
Right. Well, yes.
Yeah.
That would, in order, we'd have to develop some kind of teleportation device, and that's not really our field.
Yeah.
So but that would be great to figure out something.
Another thing is reimbursement. Collecting receipts.
Collecting all the receipts for when you're traveling.
Yeah.
And I hate that too.
I wish I think that's achievable. Like
making that
university
problem
admin
disappear
can make it more streamlined.
I guess
if anybody's listening who also has some power.
I agree that problem is more solvable than the time than instant teleportation from one location to another.
Yeah, if the Earth was flat, that could actually solve the first problem.
Yes, I guess.
Yeah, then we're all in the same time zone.
Then we'd all be in the same time zone, so we don't have to. Then jet lag isn't an issue. You still have to travel though. Travel is still awful.
Yeah,
you still have to get on the plane. Of course, you get to the airport 15 minutes before the plane.
Problem.
Anyway, so then let me go on to the next question, because you answered that one. All right, so what would you say then was the most challenging part of getting to where you are in academia?
That's a good question. I have to think. To be lucky enough.
Yeah.
Yeah.
A lot of it is just...
It's luck.
Yeah.
Yes. Don't you think so?
I agree. I mean, it's funny because you experienced... it's kind of similar to the very first thing you said, where there was only one astronomer allowed per province, per university.
Yeah. You can say, perseverance is important.
Right. But then,
but there's a lot of luck involved, right? I think I had a really amazing advisor at Columbia.
Mm-hmm.
I know there are brilliant students, not at Columbia, but
there are brilliant students at Columbia.
There are brilliant students who chose the wrong advisor, either because it's not a good fit, or
you don't know when you're a grad student. You showing up, you don't know who is going to be the right person to work with,
or they chose the wrong field to be working in, and then it's really hard for them to make it later, right?
Yeah, even if they have
they can be
lots of aptitude,
very smart and driven, and everything.
So a lot of that. So that's luck.
A
lot of that. So there is a lot of luck involved. And then, like you said, when you're applying for faculty jobs, you're competing with hundreds of smartest people in the world.
Yes.
For one job. So it's not. It's maybe not too far off from your, one astronomer allowed per province. It still is a weird, really crazy.
I don't think they told me explicitly, but that's just
what
the statistics I sort of figured out.
Okay.
And I had
another. I didn't mean. Yeah. Okay.
Yeah. No, it's fine. I had another classmate from the same province.
Yeah.
Who also put astronomy as the first choice, and we both ended up in atmospheric science, and we decided it was probably because there was another person from that province that scored higher than us.
I see.
Yeah.
Okay. But I was just sort of drawing a comparison because it seemed wild when you said that to me. But then once you get to applying for faculty jobs, it's not that far off from like how competitive it is.
And how little control we have.
Exactly.
Right.
How little
and
control
also we both got the jobs during COVID, and there were many places that canceled hiring.
Yes.
So we're both lucky in
we
that
are
sense.
both very lucky to have gotten our jobs when we did. All right. Okay, that's enough about you. We'll kind of transition to talking about science. So, when you meet a new grad student or a fellow scientist, and they ask you what you work on, what do you tell them?
It's harder these days. I work on a lot of different things, but I'll usually tell them I work in the general field of galaxy evolution.
Okay.
And I mostly do theoretical work and numerical studies.
Theoretical work on galaxy evolution. So understanding how the galaxies grow and evolve, and why they look the way they do.
Yeah.
And then you said theoretical and numerical. I want to be clear, just because I'm the host doesn't mean that my listeners know what numerical means. So what do you mean by that?
Yeah. I think the way I explain it to the general public is I set up models on a computer and see how a model galaxy or a model universe evolves.
Right. And like you were saying before, that's a lot of fluid dynamics, because galaxies have all these gas and how they move is basically it's not like when people hear fluid dynamics they think water a lot of times, but yes, it's like it's gas. Gas and dynamics.
Plasma.
And so but when we look at them on those large scales, we think of it as behaving like a fluid. And so then when you can use the equations of fluid dynamics to figure out how these things are going to evolve and how they're going to under different I guess conditions. Okay, so what would be like some example of that? Can you think of it?
So a simple example, which is like a little pet project I did, was to simulate the wind coming out of an old star and how the wind interacts with the surrounding interstellar medium.
Okay.
And I was more specifically looking at a star that is like this star that we, actually we humans have been observing for a long time, called Mira.
Okay.
So have you heard of Mira?
I haven't heard of Mira.
You have not.
I know, I'm not
because you didn't go to Columbia.
I didn't actually.
Well, no, there's a sorry. There's a professor there.
At NYU they don't teach us about Mira.
Yeah, so there's a professor at Columbia who was part of the team that discovered the tail of Mira.
The tail of Mira.
Yeah, Mira is a star with a tail.
Oh. I'd never heard of this.
Yeah.
It's a star with a tail.
You're going to have to Google it.
Okay.
Mira. I think Mira stands for miraculous.
Okay.
Yeah,
so what is this tail?
It's a miraculous star. The tail was actually so David Shimonovich was part of this team that discovered Mira's tail. So it's like completely accidental.
It's like a comet tail type thing? Okay.
It's a star that looks like a comet.
Okay. I don't know why I don't know about this, but okay, go on. It's because I didn't go to Columbia. Anyway.
So he had a poster of the star, I think probably on his office door or wall.
Okay.
So everybody there sort of is aware of the existence of such a star.
I see. That's why you say I would know about it if I went to Columbia.
Yes.
It wasn't a dig at
NYU. This is, I might not be able to shut up about Mira because it's so interesting. So the tail was discovered by a UV telescope. Okay. First, this is an AGB star, and you can't ask me what AGB stands for because I don't remember.
You just throw it out there.
Blah giant.
It's a giant
star. Yeah. So it's what the sun will turn into in 5 billion years.
Okay.
Or so.
So it's an old evolved
star. Probably the same size as our sun, like in terms of mass.
Right.
So it's exactly what the sun is going to turn into.
It's going to turn into. It's going to puff up.
Yeah, it's puffing up. It's shedding.
Okay.
But it's very different from the majority of the stars in the Milky Way. So the majority of the stars in the Milky Way move happily together in a disk.
Okay.
So the relative speeds are small.
Oh, I think I see where this is going, but go on.
Mira is a special star that moves at 100-something kilometers per second, zooming through space, basically.
Okay.
And it's also zooming through a special part of the space. It's within the local bubble. So the local bubble is this really hot bubble that presumably was created by not just one supernova explosion, but multiple.
Okay,
but
so sometime in the past there was a bunch of... This is a lot of concepts to get through at once.
As you can probably guess, the local bubble refers to the bubble we're located in.
Okay,
so
right.
we're in the local bubble.
There's a local bubble, which is like sometime in the past there was a lot of stars that died and had supernovae, and those supernovae exploded
and created this really hot bubble.
Okay, and then we can still see that is there today.
Well, we're in it.
We're in it.
Yeah.
Okay, well, okay.
Yeah, you didn't know that? You didn't know we're in a local bubble? Could I have guessed?
Yeah, I went to NYU, but anyway,
we're in the local bubble. The local bubble.
Okay, and so this star, Mira, is also in the local bubble.
Yes.
Okay.
And it's moving really, really fast.
Okay.
So then the run pressure from the gas in the local bubble is pushing the wind from the star to the back.
Okay, so
to form a tail.
So the direction of the tail is opposite the direction that the star is moving.
Yeah. So
it's
kind of like a comet. Yeah.
The comet, it's different. The comet tail point. Okay, comet.
Right.
I don't know much about comets. I knew that there was a cometary tail pointing away from the sun.
Yes.
But there's another one pointing.
Yeah, I think so. Okay. There are two tails.
Okay.
Yes.
I didn't know that.
Now you know.
Okay. I'm learning new things all the time.
See, you're growing as a scientist.
This is bad.
Have you seen a picture of a comet?
Yeah, but usually I only see one tail in the picture. But maybe I'm not looking at the right pictures.
Yeah.
Anyway, I saw what was it, Hale Bop or whichever, the one that was in when I was a kid. I saw it.
Cool.
And I only saw one tail on that, but it was by eye. So
okay. Yeah.
Anyway, so I may edit that if it wasn't the right comment. But anyways, but yeah. So the point we're getting back to
the tail. Yeah.
Yes.
So this star is very interesting to me for a lot of reasons. Well, first, I think it's interesting on its own to start with a tail. But it's actually relevant to something that I've been really curious about for a long time. It's about dust.
Okay.
So I like dust. Well, okay, I don't like dust, but I think dust is.
You played with dirt as a kid.
But not dust.
But not dust.
Dust
is different, especially when astronomers call
dust.
Is
different. Yeah. And as far as we know, most of the dust in the local universe is made in the winds of these AGB stars.
Oh.
You didn't know that?
Most of the dust in the galaxy.
So it's possible that there's additional growth in the interstellar medium, which might account for more of the total mass.
But most of it is made
to form dust. Yes. Most of the dust is formed
from stars that are like the sun at the end,
so
near
one
the
day
end of
the
their
sun
lives.
will be making dust.
Oh.
You didn't know that?
I don't.
Where did you think dust come from?
Well, I don't know. I didn't think about it. I always thought it would just sort of self-assemble, like you get.
Really?
Well, it does in protoplanetary disks. Dust will. But the initial seeds for that dust are formed from things like AGB stars
and supernovae.
Yeah, I knew that the elements that make up the dust are formed from like stars, and supernovae.
Yeah, in order to form dust, you actually need very high densities, very special environments.
I see.
And as far as we know, you either form dust in supernova, and in fact, Danny here.
Danny Milosavljevic.
Yeah. He can show you some really interesting observations of dust formation and destruction in supernova remnants.
Okay.
Yeah.
All right.
But we don't have that many supernova explosions in the Milky Way, so a lot of the dust is likely created in the winds of AGB stars.
Oh.
And I was interested in finding out what happens to dust after it's created, not in the Milky Way, but in a massive galaxy.
Oh, okay.
And or galaxy clusters.
Okay, so on much bigger scales.
Yeah, and there, interestingly, if you think about it, all the stars are moving at high velocities. So all of the AGB stars in massive galaxies should look like Mira.
So they're all, you say they're all moving at very fast
Hundreds
velocities?
Of kilometers per second.
100 kilometers per second.
With respect to the surrounding gas.
With respect to the surrounding gas. And why is that? So when we think of stars in the Milky Way, most of the ones we're looking at,
they're moving together, rotating together with the whole disk.
With the disk.
And the disk also has gas. Everything is rotating together within the disk, more or less, right? Okay. There's the relative velocities on the order of a few to maybe 10 kilometers per second.
I see. But you're saying in these more massive galaxies, the stars are moving, they're not moving
300-400 kilometers per second.
Relative to the gas. So they're not co-moving with the gas.
Well, there's not a coherent motion. I see. Right? It's all random motion.
Okay, so that's the argument why actually Mira is probably what most stars.
Yeah, most AGB stars would look like
near the end of the gas.
Yeah. Of course, it's impossible to directly observe any of them.
Right.
But I was interested in what happens to dust when it's formed in the wind and then it's immediately stripped.
Okay. Oh, I see. So, so when it's formed in the wind and immediately stripped, what do you mean by that?
Well, the wind is stripped to form a tail because the star is moving so fast.
Because it's moving so fast, it hits the gas that it's moving.
Yeah.
The wind hits the gas that it's moving with.
Kind of like when you're blowing your hair with a hairdryer, then your hair goes to the other side.
But you're saying that process that when you create shock waves and that and a lot of that dust will get destroyed?
I don't know. Maybe.
Okay. And so you're trying to understand, or that was something that we would like to understand.
Yeah, I was just curious about it. Okay. And then, sorry, this is a very long answer to a simple question.
I don't remember what the simple question was.
I should have used supernova explosions. Sorry.
It's okay.
I can still talk about supernova later.
It's all right.
Way easier. But okay, so you asked me how I would
just an
approach a question with numerical simulations.
Right. Okay, right.
So then I said, sorry, it's a very
How do you? Yes.
So. So I basically set up a wind tunnel simulation.
Okay.
But normally people would have a wind tunnel simulation with just a cloud in the simulation domain, and then you blast some wind on this cloud to see what happens.
I know, you're looking at your watch because you got a plane to catch.
It's okay. I'm all right. I want to talk
how do I explain
Mira?
this really quickly?
Yeah, I need to talk about Mira.
Let's get this done with
Finally,
fast.
someone is listening to me when I talk about Mira.
But anyway, you have a wind tunnel, and
this time I put a star in there that just keeps
blowing
supplying.
Wind. And you ask, what does that
mass.
do?
Yeah.
And it makes a tail, I guess.
It makes a tail that looks like Mira.
Okay.
And then I also found out that there's actually additional cooling in the tail. So as the tail material gets mixed with the surrounding hot gas, some of the hot gas actually cools.
Oh.
Yeah.
And do we see that, or do we have any way of seeing that in Mira? Or
interestingly, we don't really know what is shining in the UV, as far as I know.
Right.
Because it was detected by Galax, which doesn't have good spectral resolution. So we know it's UV. And normally you might say, oh, UV, that's really hot stuff.
Well, Maybe, yeah, I guess.
Right? If a star is very bright in the UV, it's usually a very hot,
Right.
Big star.
Right.
In this case, we think that it's actually the molecular gas, or at least that's in the current interpretation.
It's the cold gas that might be making this bright UV
Yes.
tail.
Yeah.
So that might
anyways.
be the actual thing we're seeing.
Yeah. In the
Okay.
UV, yeah.
All right.
Well,
But anyway,
I think
that
that's
was
enough of Mira.
That's fine, but that gives an example of okay, if you'll have your code that can solve these equations of fluid dynamics, and you can use it to explain, for example, what the star blows this wind
and
of gas
Mira
and
has a tail that long. So if there's no cooling,
right.
additional cooling, then Mira would have a short tail.
Oh, okay. So you can actually say use the length of the tail to give a sense of how what's going on in what kind of processes are going on. So that's very cool. Okay. So then let me ask you: is there an example of something that you think is like a research accomplishment that you're very proud of, or that, or something that, or just something you're excited about right now?
Yeah, turbulence.
Turbulence. Okay, I know you give me a look like, can I say turbulence? And well, most people's experience with turbulence is it was on planes, and it's bumpy. So maybe we could try to explain what physicists think turbulence is.
Yeah. What do you think?
What do I think it is?
Yeah.
Well, you have some fluid, and that you say maybe like take some fluid and you stir it with a spoon, and then it's like
coffee.
What?
Coffee.
It's like coffee. Okay,
yes,
you stir coffee.
When you pour some,
you might stir it in a large circle. Let's say you stir it in a large circle.
Yeah.
But then you also get a whole bunch of littler.
Yeah, you don't really put milk in your coffee, sorry, but
well, if you put some,
but you can imagine if you were to pour milk in the coffee, then you stir it up and you see these big swirls turning into little swirls, that's basically turbulence.
And that's basically turbulence. So when you have, it's what they call a cascade.
Yes.
From these large scales to the small scales, and so you're interested in how fundamentally how that works. It's a very deep question that we've only made minor progress on in the past century. In my opinion.
Yes, and most of that is about the kind of gas that we deal with on a daily basis, right? And there's a lot of brilliant engineers who have really studied turbulence and made a lot of progress, but that's for the kind of gas we're familiar with, or fluids we're familiar with. But sometimes for us astrophysicists, we're dealing with plasmas that just simply cannot be studied in a lab. So for example, if we're talking about the stuff in the intercluster medium, or actually even just the stuff in the local bubble, I would assume the density is so low that you just simply cannot recreate that in a lab.
Oh, I see.
And it's also, so because the density is so low, the mean free path of the particles, meaning the...
It's okay, you say the sentence and then we'll go back.
How long a particle travels before it hits another particle is extremely long. So in the outskirts of galaxy clusters, the mean free path of the electrons is on the order of 10 kiloparsecs, so the size of a whole galaxy.
So an electron can travel the whole galaxy before it interacts with anything else. Without hitting it.
Without hitting another particle.
Okay.
But obviously, there are also magnetic fields, so then these particles will also interact with magnetic fields, which can
bend their path.
Theoretically, yes.
Okay. But anyway, sorry, the point you were making is that these are the types of things that we don't have the ability to do in a lab.
We don't have the ability to study in a lab, but we think there's possibly turbulence there.
Right.
And
why not? Why shouldn't there be, right? If things get stirred on these really, really large scales.
Yeah.
So you would expect.
Yeah, but we also don't understand the small. Well, when we say small scale, it's actually large scale. But depending how you look at it, right? We don't understand dissipation of turbulence in these environments.
So when you say dissipation, you mean like
normally in this room, dissipation happens at scales close to the mean free path, where particles are no longer colliding with each other.
So
you
dissipation.
Having,
okay.
Yeah,
so in other words, if particles can't collide.
Yeah.
So the whole point is
you can't make a swirl anymore.
There's like 10 concepts in there that we have to like untangle. It's okay.
Just cut it.
That's. Well, then don't just. I didn't say that sentence then. But I guess your point is okay. So normally with turbulence, you stir something at these really large scales, and then it turns into like smaller whirls, and those whirls turn into smaller whirls, and then it keeps going down
all the way
cascading
until at the very small scales.
And these very small scales, then something like viscosity will remove that. Will take away the energy from those
turn it into just heat.
Right.
Yeah.
And
or random motions of little particles.
It doesn't just happen directly. You stir something large, and then it cascades all the way down to those small scales. Yeah. And so that dissipation process, what you're saying is that requires viscosity, things like that, require particles to interact with each other.
Yeah.
And if an electron travels the whole galaxy without interacting with anything else, without colliding with another particle,
directly colliding with another particle,
how do you have anything dissipate?
Exactly.
Okay.
But we think because all the particles are interacting with magnetic fields, then effectively they are still interacting with each other.
I see.
Through the direct interactions with magnetic fields.
I'm kind of afraid to ask this question, but how do you even probe that? Like, how do you determine whether that's what's going on?
It's very difficult. So I think what I'm very proud of is I did some observational work, and it was really outside of my comfort zone
because you're a theorist.
Yes.
You normally stay at your computer.
Yes, I run models, and if models are wrong, it's fine because people would make that assumption about your models. Anyway.
People always assume you're wrong until you until it turns out to be right.
And when you're dealing with the real data, there's a thrill, but there's also the fear.
There's the fear.
Yeah, there's this thrill because this is the real data. This is the real universe.
Right.
But there's also the fear that you're not actually extracting the right kind of information about this real universe, and you're misrepresenting what the universe is trying to tell us.
So that's kind of scary.
It is scary. And there are many, many, many observational biases that we do not understand.
Right.
Or cannot understand.
But in any case...
you were
regardless, it was exciting, and you did this actual observations of turbulence.
Yes, in galaxy clusters.
I think
it says something interesting about how turbulence behaves, maybe. I think the results are very puzzling still.
Right. And so in other words, we won't get into the details of it, but like turbulence, like in a laboratory or in this room, behaves in a certain way that we think we understand in a broad strokes. But the turbulence you've observed in galaxy clusters doesn't seem to obey that same law. In other words, how much energy is in whirls of different size, it's different than it would be, and then we don't really know why.
We don't.
So that's exciting because we don't have an answer yet.
Yeah, and it's also really hard to study this on a computer, right? So we can make assumptions and just run fluid simulations, but because we're dealing with this very low density plasma that is technically only weakly collisional or hardly collisional.
Right. We don't. There's very few collisions that actually happen.
So the fluid approximation actually theoretically breaks down.
So
because
it might even be wrong to think of it as a fluid.
Yes,
and we
it
don't
might
know,
be wrong.
we don't know how wrong it is.
But if it's still okay to assume it is fluid, because if we assume there's enough interactions between particles and magnetic fields, and all these plasma instabilities are operating to help enhance the effective collisionality. So if we can assume that effectively the plasma
one way or another
still
it behaves like a fluid,
then this will be a fluid with extremely low viscosity.
I see.
So low that we again cannot study it in the lab.
We can't study in a lab, but low viscosity should be very good, because it means that you have large separation between the largest scales that it's stirred on and the smallest scales.
Even on a computer, I think it's hard to achieve this kind of Reynolds number.
Yeah, sorry. You don't have to say the word Reynolds number, but it's hard to achieve that.
Viscosity.
Right. Because just because on a computer you can only have so much of a range of scales, of length scales that you look at once.
Yes. So it's interesting stuff.
Yeah. Okay. Well, that's great. I like that your answer didn't have a conclusion to it. It's just we still are puzzled about it. It doesn't behave the way we think it should, and we're still figuring it out.
Yeah.
Okay. Very good. Well, I know you have a plane to catch, so I'm gonna wrap it up now.
Okay.
So thank you so much, Dr. Li, for indulging us, and I had a lot of fun talking science with you, and I hope you join us again sometime.
Oh, thank you, Dr. Paul Duffel, Professor Dr. Paul Duffel, for having me here.
You're welcome. All right, great.
It's always good to see you.
One of the many things that Yuan and I debated about offline is just how early you should arrive at an airport before grabbing an airplane. I am always way more paranoid than she is. I always have to get there 2 hours early, whereas she doesn't mind strolling in just before the plane takes off. Anyway, I kept panicking there at the end because she had a plane to catch, but she seemed totally unfazed. Regardless, thank you again, Dr. Li, and thank you to our listeners. We will see you next time. The Astrophysics Podcast is supported in part by the National Science Foundation under grant number AAG 2206299. The music you're hearing now and all the music on the Astrophysics Podcast was written and recorded by Britton Ashford, and you will find it on her album Trotter. All songs are used with permission from the artist and producer. Please look her up if you enjoyed it. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, Professor of Physics and Astronomy at Purdue University.